So in this video, we would like to discuss continuous maps between metric spaces. And first of all, we have the classical treatment of continuity. So suppose that we have two metric spaces. So let x comma d sub x and y comma d sub y are two metric spaces. And f from x to y, a map, a function, meaning a associating with each x from x a point y in y, or a point in y. I don't know why I have to call it y. Anyhow, so the classical description of continuity is how at a given point. So first of all, one starts with a given point. So let's say that this is the point x, and this is the point f of x. So basically what we're saying here is we want the inputs that are very close to x to have outputs that are very close to f of x, and mimicking the standard definition of continuity for functions over the real numbers, which is actually based on the definition of the limit. We say that for any ball, open ball with radius, let's call it epsilon, that surrounds f of x, we can find a ball with radius delta in x, so that the whole ball in that is centered at x maps into the ball that is centered by epsilon. So this really means that if you want the outputs to be epsilon close to f of x, you'd better make sure that the inputs are delta close to x. And no matter what epsilon you give me, I can always give you a delta that works that way. So let's write this. So f is continuous at x if for every epsilon greater than 0, there exists delta greater than 0, such that if the distance between, or there are a few ways to put this, but you can say if the distance between a and x is less than delta, then, and this is the distance in the space x, then the distance in the space y of f of a comma f of x is less than epsilon. I know it's more traditional to actually denote the center of considerations by a, but you know, I hope it's not a big deal. And there is a much better way of saying this. Equivalently, for every epsilon greater than 0, there exists delta greater than 0, so that, and here's a very simple inclusion that tells the whole story, and actually underlines how it's so much easier sometimes to express things in this more abstract context. So the image of the ball in x of center x and radius delta maps into the ball in the space y centered at f of x with radius epsilon. Okay, so I just used the subscript x and y in order to specify that the ball is considered in the space in the corresponding space. And of course, let's recall that by this notation we mean all z's in X, such that the distance from X is less than delta. Okay, so my claim here is that there is a way to actually express continuity in an even more seamless way if we want to just refer to maps that are continuous at every point. And this will be the case. So this will work very nicely for us. So we say that f from X to Y is continuous if it is continuous at every X in X. Okay, and here comes the interesting, I wouldn't call it exactly surprise, but it's a very nice way of expressing continuity. So proposition here, you will see I don't even need to specify the metric. So if X comma Y are metric spaces, then f from X to Y is continuous. Again, I'm interested in continuity at all points, which is again the usual case. Sorry, then f of X is continuous if and only if for every V subset of Y open, the inverse image of V is open in X. Okay, and of course here, let's make sure that we all understand what we mean by inverse image. Inverse image are all the X's in X such that their output through F belongs to V. This could potentially be an empty set, obviously, as you can understand, even if V is non-empty. So this is the characterization, and in most cases, after a certain point, when we go to the next level of abstraction of topological spaces, this can be taken to be the merely the definition. But since it's our first exposure to this kind of concept, let's prove it. And again, since it's an if and only if statement, as you can see here, this means that we have to prove two directions, right? And both directions are what we say, what we call formalities. I mean, there's nothing, creative about this proof. We just chase definitions. So in commutative algebra, sometimes we say that we prove things by chasing diagrams. My favorite way of describing such proofs is that you just chase the definitions around and pretty much everything everything falls in place. And this is why you can always consider this as a translation of the notion of continuity in to a different kind of terminology. So in any case, let's see how this is done. So assume first that f is continuous. So let f from X to Y be continuous. And V subset of Y open. Then we want to show that f to the negative 1 of V is open in X. We need to show that f to the negative 1 of V is open in X. And of course, if this is empty, there's nothing to prove. The empty set is vacuously open. It's considered to be open because remember the definition of an open set says for every element in that set, blah, blah, blah. Well, if there's nothing in that set, then certainly that definition checks out. Okay, it's the coldness of mathematical logic, if you like. But in any case, if this is empty, we're done. If not, then we will need to show that for every X in this set, there exists a delta. And you see, by saying delta, you know where I'm getting with this. There exists a delta greater than 0 so that the ball centered at X with radius delta is a subset of this. That's what it means for a set to be open, right? That along with any point that comes with a set, there is a open balls centered at that point that also comes with our set. So, okay, so what is the simple idea? The simple idea is that now if you look at f of x, since V is open, so since V is open, there exists epsilon greater than 0, so that the ball centered at f of x with radius epsilon, f of x has to belong to V, right? I mean, that's what it means for x to belong to the inverse image of V. And this should be a subset of V, right? That's what it means for V to be open. So now we apply, obviously, and that's why I use this epsilon and delta, to apply the definition of continuity. By the definition of continuity, there exists a delta greater than 0, which is the delta we were looking for, such that the ball centered, the ball in X, if you like, centered at X with radius delta maps into the ball in Y, centered at f of x with radius epsilon. But since this whole thing is inside V, so this whole ball is inside V, that means that this, but then this ball is a subset of the inverse image of V, and that does it. Here, just to be consistent, let me just put a subscript on all balls that appear, because it wouldn't be fair to have some of them with subscript and others. But the subscripts are easy. If we're talking about balls in X, the subscript should be X, and if you're talking about balls in Y, the subscript should be Y. So I think we're all set. Like I said, we're just chasing the definitions. And let's go the other way around, which is not going to be any more thrilling. And So what is the premise now? Let f from x to y be such that the inverse image of every open set in V is open in X for every open set V in Y. Okay, then we will show that F is continuous. And we will do that by showing that it's continuous at every point of X. So let X in X, we will show that F is continuous at X. And what's the idea here? The idea now is very simple. Let epsilon be greater than 0. We need to find delta greater than 0 such that the image of the ball in X centered at little x with radius delta is a subset of the ball in Y centered at f of x with radius epsilon. And here's how this is done. This is so simplest. Well, note that the ball with radius epsilon centered at f of x is an open set. So by our assumption, the assumption was that is this one, that the inverse image of every open set is open. So the inverse image of b sub y of f of x is open in X. Yeah, but little x belongs to that inverse image. And so since this set is open, and hence there exists delta greater than 0 such that the ball in X centered at little x with radius delta is a subset of this open set. Yeah, but what does that mean immediately? This implies, so that tells us that if that everything that is in this set has its pre-image in, or I'm sorry, everything belonging to this set is also the pre-image of something that belongs in here, right? So this implies that all the elements of the ball of radius delta centered at x maps into this ball, which of course checks continuity for x, i.e. F is continuous at x. And because this goes any x, it's continuous on all of x. Thus, f from x to y is continuous. And this is pretty much what we use from now on as the definition of continuity, or it almost acts like the definition of continuity. Also, there's another very interesting thing to consider here. In general, if you take a set B, the inverse image of the complement of B is the complement of the inverse image of P. Okay, this is something that can be checked really easily. And this tells us that since complements of open sets are closed sets, this implies that f from x to y is continuous if and only if for every closed set K, which is a subset of Y, the inverse image of K is closed in X. There are actually more equivalents of this definition, so we just gave two. But I think these two are going to serve us well, and we're going to leave it at that. So, thanks for watching.